Pleasure to introduce today's speaker, Stephan Schlamminger from the National Institute of Standards and Technology in Gaithersburg, Maryland, who's going to present his work on measuring big G, or the gravitational constant. Here we go. So Stephan is many things. I was on a conference call this earlier today with a colleague who I think described it perhaps most succinctly. He's a guy who travels the world doing really hard experiments, in particular precision measurement experiments. Stephan has the distinction of having his name attached to two, arguably three, of the so-called code data, which are the constants that we find at the end of textbooks, including two entirely different measurements of big G and the latest measurement of Planck's constant. He's also infamous actually for reporting measurements of these fundamental constants blindly at conferences, which means he doesn't analyze his data until he's actually giving the PowerPoint presentation, which is probably one of the ballsiest things you can do as an experimentalist. So how did Stephan get here? Stephan received his diploma in physics from the University of Regensburg in Germany in 1998, his PhD in experimental physics from University of Zurich in Switzerland in 2002, where his thesis was on the same topic we'll hear about today. From 2002 to 2010, he worked at University of Washington on the famous Eöt-Wash experiment, where he performed what was understood for a long time to be the most precise test of the equivalence principle. In 2010, he moved to NIST, where he began and he continues to work on the Watt balance for determining Planck's constant. I think the most precise measurement they've made is 1 part in 34 billion, I think. So he actually has a tattoo, I think not with that many digits, on his arm, if you want to see the last few digits of Planck's constant. We became the group leader of the Fundamental Electrical Measurement Group at NIST in 2016. From 2017 to 2018, he taught physics at Regensburg in applied science, and since fall of 2018, he's been working under the title of physicist at NIST on topics related to the realization of the unit of mass and impedance measurements. So Stephan works closely, or at least obliquely, with three faculty at the OSC at least, including Felipe, myself, and our new faculty member, Chris Panda. So I hope this is the first of many visits, Stephan, and I leave the podium to you.
All right, thank you, Dalton. Yeah, it's a weighty CV, I know. All right, so who has heard of NIST? Oh, that's pretty good. That's, I would say, 42.5%. So what do you guys think I'm doing at NIST? I'm trying to get inspiration, so I know when I go back what I have to do. Yeah, so what would my typical work look like? Well, that's right. Can I show you? It's this. So I work at the intersection of mechanical experiments and electromagnetic experiments, right? Okay, so this is precision mechanical stuff and electrical stuff. So we did this Kibble balance is used to measure Planck's constant, is now used to realize the kilogram. We have a machine that can realize torque. We measure photon pressure, all kinds of stuff. And today I talk about the measurement of big G because it makes a nice story. All right, so this is a play that I tell in 3 acts. So the first act, I talk a little bit about a little bit of history, how we know stuff about gravity. And then I tell you how people try to measure the strength of gravity, and then I tell you about this particular experiment, this BIPM experiment. Okay, let's start with the brief history of gravitation. Let me go back 2,100 years or so to Ptolemy. So he looked at the 7 movable stars, right? So there were the 5 planets. So we have the 2 inner planets, Mercury and Venus, then Mars, Jupiter, Saturn, Sun, and the Moon. These were the only things that were moving in the sky. All the other stuff was supposedly fixed. And he was trying to understand how they move and measure them. And he could actually come up with a model that predicted their position in the sky with an angular position of about 2 degrees. It's pretty amazing. And the reason it was so good is because he measured it, and then through the periodicity, he could average the measurements and get better and better with the model. Okay, the model was relatively simple. It was just these epicycles, so circles with constant angular velocity on circles themselves. So rotating circles on rotating circles. And one trouble was, for example, Mercury had a relatively big eccentricity, and that was difficult to get right, but he could get it right. So he had a relatively good model. 2 degrees was as well as he could do. So that was pretty good. So we needed a better model. So then the next model is about 1,500 years later. There was a guy, Tycho Brahe, and he said, "Man, we should be able to measure this much better." And he dedicated his whole life of measuring these positions of these planets 10 times better than we know at the time. So, and this was before the invention of the telescope. You guys should know when the telescope was invented, right? I mean, optical sciences. So before the invention of the telescope, he could measure these positions of these planets to about 1 minute of arc, right? So we had 2 degrees before. Now we are at a 60th of a degree, right? So there's a factor 120 improvement. But it cost a little money. It cost about 10% of the GDP of Denmark. Yeah. So, he had multiple clocks, timekeepers. I mean, this is a pretty big operation. And he had his own model that he wanted to prove with the data, but he never got there because he died relatively young. He died at 55. And, Denmark would have wasted all this money if there wasn't the guy who stole the data. And this is Kepler. So Kepler also had an idea of a model. He said, "Oh, I have this very, very idiosyncratic model, but I need data to prove the model." And he knew that Tycho Brahe had the data. So he hired on with him in 1600, and it happened a year later, Tycho died. And I don't think it's anything to do with the other, but it's just, or at least that is what's believed. And, yes. I don't know the detail, but he also left Denmark later on and went to Prague, right? He wasn't, at some point, he was not welcome to Denmark anymore after spending all this money on measuring planetary positions. So Kepler analyzed Tycho's data for about 9 years, and he condensed it down to 3 rules, which is kind of nice, right? He can 10% of Denmark's GDP give you 3 rules at the end, and we know the 3 rules, that the planets move in elliptical orbits, and we have the third one is the most famous one, t²/a to the third is a constant. So you're almost at the law of gravity, because now with this step, it took Newton to realize, well, if Kepler's laws apply to the planets, it also has to apply to the apple, right? If the apple falls down, this must be the same rule, so I must be able to apply this. And he came up with the law of gravitation as we know it. And, there's no big G in here, right? And who has read Newton's Principia? Well, I tried it. It's very, very difficult to read because he doesn't use modern math. Everything is in relations. Everything is in ratios. And it's very, very difficult to comprehend with normal formalism. So it's very difficult. But this is how he basically said there's a force that's proportional to these 2 masses and the radius squared. And it took until 1811 until Poisson realized we should add a proportionality constant. And then big G was introduced by Koenig and Richards in 1885. And we will get to this in the second act. Let me finish the first act because I want to finish the story of gravity. So as we know, Newton's theory of gravity is a big success, right? I mean, but it has a few shortcomings. Let's start talking about the shortcomings first. So we can only solve the 2-body problem, right? With perfect symmetry, right? It has to be perfect spherical bodies and stuff like this. So we can't even prove if our solar system is stable, right? That's not possible to prove. I mean, there's people doing numerics on it, and it has been around for a while, so it probably is stable. But it's not difficult. It's difficult to prove. But because of this, we have perturbation theory, numerical integration. All that stuff was developed in order to apply Newton's theory of gravity. And one of the big culminations was the prediction of Neptune. Neptune was predicted, and then Gall looked at it. Yes, here it is. So it's really beautiful. But back then, not everything was dandy. There was one problem, one very nasty problem. And that had to do again with Mercury. We know that Mercury has this big eccentricity, but it also has a perihelion shift, right? So if you draw a line from the sun to the closest approach, this is what we call the perihelion, and that perihelion moves around. Guess how much it moves? A minute of arc per century. That's pretty good. It's pretty good. It's 10 minutes per arc per century. So here you see this. If you add this all up here, 531 arc seconds per century. And we know where the stuff comes from mostly, except 43 seconds of arc. These 43 seconds of arc were just unexplainable. We couldn't figure it out. And people thought about it, and they came up with proposed solutions, and you will not be surprised that these proposed solutions sounds very familiar than we had before too. Oh, there could be some mysterious dark planet that's behind on the other side of Mercury that causes it. There could be a ring of mass particle that we can't see, some dark matter, right? Or we could have to modify the law of gravity to some concept that's not 10 to the r to the minus 2. It's just a little deviation from that. All the stuff came up, and people tried it, and they couldn't figure it out. And then the solution came totally out of left field, okay? There's just some guy sitting in a patent office on a chair, and he said, what would happen if I turn gravity off, right? And then he realized, well, then everything would drop with me. So a free-falling observer, there's no gravity, right? What gravitation is, it's just another way of thinking of an accelerated reference frame. Okay, so this is very similar to Galileo thought, a body that moves with uniform velocity, there's no force on it. And that's, I think, in the same philosophical vein. It's just, the acceleration picture of it, right? Acceleration and gravitation is the same. So he came up with this, what he called the happiest thought that he ever had. And this is the equivalence principle. And with the equivalence principle, you can explain a lot of stuff, right? So there are 3 classic predictions, the perihelion shift of Mercury. So we now know this 43 arc seconds that people couldn't figure out is now explained. We could explain the deflection of light by the sun, and that was then figured out, a couple of years later by Eddington. There was a solar eclipse on the South Pole, then he traveled there, and sure enough, the apparent positions of the fixed stars behind the sun were different than when the sun is not in the field of view. And then the gravitational redshift that was then shown by Pound and Ripke in the 1960s. There's still some interesting problems with this, right? But let me show you. This is the Einstein equation. This is the full model if it's a nonlinear equation, if you want to solve all the stuff. But for most things, the equivalence principle is good enough. The equivalence principle explains the perihelion shift, deflection of the light by sun, and the gravitational redshift. Sometimes you get the answer wrong by a factor 2, but you can get the right idea. And this here, where we see a big G again, is the stiffness of space-time, right? So this is the curvature of space-time. This is the stuff that's in space-time, energy, mass, and so forth. And this is how much the stuff deflects space-time. I should get a little drink of water. But there is, of course, a problem. And one problem is if you look at this, then you see that this one here is a continuous quantity. And this is a quantized quantity because we know matter and energy is quantized. So how can you relate a continuous quantity with a quantized quantity? And this is the problem of quantum gravity, right? The other thing is, when Einstein wrote down the field equation to describe the universe, he introduced something which was the cosmological constant, which he later on said is the biggest blunder of his life. But it turns out we need that to understand our universe, right? Because there's only about 5% which is made out of the material that we know of. Then there's the dark matter, which changes the rotation curve of the galaxy. And then there's the dark energy, which is this cosmological constant that makes the universe be flat, essentially. All right, so this is the brief history of gravity. Everybody still with me here? Good. Let's talk about the strength of gravity. No. That was a prediction.
What's that again?
He predicted the bending of light. And then Eddington went to the South Pole and measured it, and sure enough, it was there.
Theory somehow will explain it, but off by a factor of 2.
So the equivalence principle can explain it. That acceleration and gravitation is the same, yeah. So here are the 4 fundamental interactions that we know, and you can, attribute a relative strength to it. So this is usually done by, you can figure out what is the attraction between, let's say, an electron and a proton, and then you can say, what would be the gravitational interaction? You find out it's about, 10 to the 36 times weaker, right? So it is extremely weak. It's a long-range interaction. And so let's make a little Gedanken experiment here in the room, okay? So suppose I turned off gravity from like this, okay? But I still want the Earth to go around the sun, right? So in order to make this happen, I need to have a steel rope that is about, an astronomical unit long. What diameter of a rope would I need? Steel, let's call it a steel rope. Well, what do you guys think? How much, what diameter do I need to have to keep that ball spinning around the sun? Any guesses? I need some guesses, otherwise the talk will stall out here. Yeah.
100
A kilometer.
mile.
A mile. Uh-huh. You have to build of units. Okay. I laid it out for you. It's about 2/3 of the diameter of the Earth. So yes, gravity is very weak in the lab, but it's very, very strong in astronomical settings, right? And we know there's no gravitational force between two everyday objects, right? But I can definitely feel my weight, right? So so me and Mother Earth, there is a pretty big bond here, right? Okay, so this is what we're talking about. So I'm talking about the Newtonian gravitational constant, right? So this is this big G. This is today's value that we know it of, and you see it's a very small number in SI units. It's always an attractive force. So I want to show you how people measured this, and I also want to talk to you about people before G was introduced by Poisson and so forth. So what did people do before? They did the following. They used an equation of little g. So little g would big G times the mass of the Earth divided by the radius of the Earth squared. Okay. So if I now add a few factors in here, I can write this as the mean density of the Earth. So what people used is, instead of big G, they used the mean density of the Earth. Okay. And you all knows how dense the Earth is roughly, right? You know that? No, it's about 5,510 kilograms per cubic meter, or 5.5 grams per cubic centimeters. Okay. So in CGS system, it's just a number that's easy to handle, 5.51. So who first knew what the density of the Earth was? We'll take this week. Who first figured out the mean density of the Earth? I tell you, it was Newton himself. So here's how he deduced it. He said, up here is air that has about a density of 0. Then there's water that has about a density of 1 in CGS units. Then there's sand that has about a density of 2. Then if I go further down, at some point I hit whatever iron density of 8, and then I hit maybe lead density of 9. So if I average all these densities from 1 to 10, so it must be around 5. So between 5 and 6 is it. No, that number stood for a couple hundred years. So then we need now an experiment, right? And I'm very proud to tell you this as a Marylander, because the first idea to measure the mean density of Earth arose in Maryland. In fact, it arose at the Maryland-Pennsylvania border. At that point, there was a border dispute between the Culvers and the Penns. And in fact, I rode my bike up there. This is the border between Pennsylvania and Maryland. So here's where the Marylanders wanted to have the border. This is the 40th parallel. The problem with this border is that Philadelphia would be in Maryland, and the Penns didn't like that. So the Penns wanted this border down here, which the Marylanders didn't like, because then the territory would be split into like 2 islands. So back and forth, there was a compromise made, and this is the Mason-Dixon line, 39 degrees and 43 minutes and 20 seconds. So Mason-Dixon came over from England, and they had to measure that line across here, right? So they started somewhere on a suburb of Philadelphia and measured across here. So what they did is they used this telescope thing, and this is how you do it. You set it up, you look at the North Star, then you pivot it down to the horizon, and you rotate it by 90 degrees, and then you basically look east. So you measure out, or west, measuring out to the west. And in order to do this rotational platform, you have to level the telescope, right? So you have a plumb line that allows you to level this whole gimbal system, right? So you basically do this procedure, you measure out, and you go then point to a tree or something, and then you measure out, usually they went about in increments of 12 miles. And then they, move 12 miles forwards, and then they do it again. But Mason-Dixon, they were not stupid, right? They were real meteorologists. They said, we should also measure backwards and see if we can back to the original spot. And, when they started out in New Philadelphia, it worked everything was peachy, everything was good. They hit here the Allegheny Mountains, and suddenly they realized that their meridian has deflected to the north when they measure westwards, and when they measure eastwards also, so they did not come back to the same spot. So they corresponded this to England, and said, here's the problem. And in England, it was Baskerville and Cavendish. They looked at the report and said, yeah, this is clear. It's the gravitational attraction of the mountains to the plumb line. This is what it is. And then they said, we could use that to measure the mean density of the Earth. And they did that. So this is the Mount Schiehallion experiment in 1774. So Mount Schiehallion is some mountain that's 1,000 meters or so. It's up here in north of Edinburgh. And it's a pyramidal shaped mountain, so it's very easy to do mass integration because it's a very nice shape. They set up a telescope on the left and on the right, looked at the same fixed star and measured the deviation of the telescope sighting with respect to the plumb line. And then they could figure out the density of the mountain. And they just thought, well, the mountain's density has to be the same as the Earth, and this is it, right? So you see that this number is low. And you know the reason why it's low? Because a mountain is like an iceberg. It's like an iceberg on the Earth's crust. It floats on the Earth's crust. So it's made out of lighter material. So if it would be made out of heavier material, it would sink, right? So that's why you measure something that's actually much lighter than the Earth, than the mean density of the Earth. So, but it was, the first experimental measurement of the gravitational constant. Cavendish was part of this expedition, and he said there must be a clever way, right? We must be able to measure this in the lab. And he was actually lucky. He had a friend, John Mitchell, who built this torsion balance. And at that time, John Mitchell and Ampere or something, they built the torsion balance about the same time, And he could use the torsion balance to measure the mean density of the Earth. And here's the measurement. It took him 5 years to measure, which is, I would say relatively quick for a big G measurement. On average, it takes 10 years. And the other thing that's very interesting is he gave an uncertainty. That's a first here for the measurement. And I will show you how this works, okay? And I'm showing you a bunch of cartoons, and you better get used to these cartoons because you see a whole bunch of those. So here's how it works. Oops, where's my clicking here? Oops. Oh, let me advance it here with the. All right, so we're looking down the torsion fiber here. Okay, here's the dumbbell. So this is what we call the test masses, the small masses. Here are the big masses. And we have to do 2 measurements. So we put the big masses on one side and the torsion balance deflects a little bit here. So this angle is some big G K1 divided by kappa, right? But you don't know where you measure that angle from, right? Because there's no zero. So you deflect it the other direction here and you get the second angle, right? So now you can take the difference, but what you don't know is the kappa, right? So you have to measure this kappa, and this is you take the masses away, you let the pendulum oscillate, you measure the oscillation frequency, and you can calculate the I. So all the red things are calculations, right? So and figure this out, you divide this and you get big G. So K1 and K2 is just a geometry where you have to integrate the torque that would be expected in your geometry, right? So this is how you do it. And it is still in use today. It's called the Cavendish method. The trouble with this method is that you have to measure angles absolutely, right? So it depends on angles. But this is the first measurement in the lab. And if we look how it went onward here, so here's a list of measurements from Newton's guess, 1687 to about 1942. And here you see the numbers. So very much all these people who measured lower, this is mostly these people who measure some floating mountains, okay? There's some where people measure very high, and this is also measured in a mine. For example, this one here, 6,600. Erie measured the change of little g inside a mine, and because there's all the lead and all the stuff around it, he measures a little higher. And here's today's value, and here you can see how close Newton's guess was, right? And this is a Cavendish measurement. So it's pretty good, right? So now we have the Cavendish measurement, and he uses the torsion balance, and you will see, I'll show you later on a plot. So the torsion balance to date is even the most precise instrument that you can use to measure big G, okay? But most people don't use the Cavendish method, they use a different one. And that was developed by a Jesuit priest, Karl Braun, is an Austrian guy. He was a school teacher for many, many years, and then he was too old to teach because he couldn't see anymore and he couldn't hear anymore. And then he started measuring gravity. And he has written this book here. And he invented what's called the time of swing method, right? And I think the time of swing method, this is how it is called in the field, but it hides something. It is actually a frequency measurement. And we all know in physics, if you can convert your measurement problem into a frequency problem, you win. Because you don't have to measure any other, stuff. You just need to count. You need to count things per second or something, or per minute. So that's nice. So here's how this works. You put the masses close by to the torsion pendulum, okay? And now what you have is you have the restoring torque of the fiber plus the gravitational spring. So these red masses want to pull the blue masses in line, so they are lined up. So you get an additional restoring property, which I call Kn. So this means this frequency is higher than the frequency over here. So here, the masses are far. In this case, I drew them so they're completely away, so Kf will be 0, but usually people just rotate them by 90 degrees, but this is just a thing, right? So you have your Kf, and you can get this. So if you take the difference here in these frequencies squared, divided by your geometric constant that you have, and the moment of inertia, you get G. So you only have to measure frequencies, and all the other stuff are calculations. Very nice, right? You will think that this is the best method ever, right? And people used it for 100 years. So it was invented 1896. In 1995, I believe, if I'm not mistaken with the year now, Kuroda pointed out a small problem. And it's kind of interesting because people have used it for 100 years and nobody had the slightest idea that this problem could be there. But in the electrical measurement techniques, this problem was already found out like 100 years earlier. And this has to do with no spring is ideal, right? Every spring has a little bit of loss. And Dahl knows very well about loss. So, what you can think about it is you have a perfect spring, and then you have a little, what people usually describe as a dashpot of a spring in series. So this is what people call the Maxwell model. So this is kind of an idea that you can think about a spring. It's not perfect, but it's let's go with it for now with me. So now what happens is if you have a high frequency, so you pull really hard on this, then the dashpot is just a rigid connection. So you get basically both of these spring constants, right? If you push slowly on this, the dashpot relaxes and you only get this spring constant, right? So if this, for example, is 10% of this, then your spring constant as a function of frequency will look like this, right? It goes from 1 to 1.1. And of course, this is a simple model, but you can make models that are a little bit more complicated where you have many of those, and then you can, it's still the same idea, right? You basically have at low frequency, a low spring constant, at high frequencies, a high spring constant. So now, if you think about this, I'm not bore you with the details. What will happen here is now this K and this K is no longer the same. They're different. So the G that you report of the previous equation is actually the real G plus some bias term. So the reported G is slightly higher than the real G. And the amount that this is higher depends on the Q of the oscillator. Okay, the higher Q of an oscillator you can build, the smaller the problem is, right? So if you want to measure G to a part in 10 to the 5, you need to have a Q of about a part in 10 to the 5, and then this is no longer a problem. But this is just something to keep in mind. Okay, so we had the Cavendish method, invented 1798. We had now the method from Brown, 1896. There's two more methods. One was invented in 1971. And this is by Jesse Beams. Many of you probably know him. He's a very famous physicist out of the University of Virginia. And he invented this angular acceleration servo system. So what happens here is you put the torsion pendulum on a turntable, and as the torsion pendulum accelerates towards the source masses, you accelerate the turntable so that the fiber does not twist. And that is a very, very elegant method, okay? Because you don't have any fiber problems. So here's my cartoon for this. So here the math is slightly different because I'm going to work in polar coordinates, but you still have this calculation, moment of inertia, and you see that the phi dot dot, the theta dot dot, this is how I have to accelerate this turntable, gets G. So there's only one measurement mode needed, not like in the other ones where I had, two modes, and it's a very compact equation. And the world's best experiment is done at the University of Washington. Jens Gundlach, he measured this with this experiment here. And he also had another interesting idea that a lot of people didn't have before that, and that is instead of using a dumbbell, so Cavendish used a dumbbell in 1798, and for the next 200 years, people are using dumbbells. And the reason is it's just easy to calculate, right? Because you have just 2 point masses at the end of a stick. But it's not the most ideal thing. If you use a plate, then if I go back one slide here, then this stuff cancels. I over Q2 is basically independent of the geometry if W is larger than T. So that was another good idea. So this experiment had an uncertainty of 13 parts per million. This is the best experiment. A few years ago, one with 11 came out, but it uses the same method. Okay, and now the last method, and that is the newest one, came out in 1987. So we have already heard that you can use a servo system to, prevent the torsion belts from rotating. So people said, why not using an electrostatic servo? And this is what these people from the PTB, so the PTB is the NIST in Germany, so this is the National Metrology Institute in Germany. They had this idea of using an electrometer to basically servo the torsion pendulum back. I show this to you also how this works here. So we have here again the source masses. They, in this case, make a counterclockwise torque on the blue balls. And now I have here these green electrodes that I apply a voltage. With a voltage, you can only pull, you cannot push, you can only pull. And so I get this additional term here. And there's another term that the Germans originally forgot because I have this other capacitance gradient between these two other electrodes here, which also depends on V1. So I have V1 on the green, everything else is grounded. Then I measure a clockwise torque, so I put the source mass on the other side and get this term. And now this is again done to cancel out the k theta, right? So whatever the fiber that you have, and to figure out the zero. And then I have to measure these capacitance gradients. So usually what I do is I measure the capacitance, the function of torsion angle, and I need to measure all three of those, and then I can figure this all in and do it, right? So this is how it's done. It's a relatively complicated measurement, and it's really difficult to get right. So here's what the Germans did. They measured it in 1987. They got a relatively good result. They rebuilt it. They get a result 83 ppm uncertainty, but they were 73 sigmas higher than the CODATA values. So CODATA is this Committee on Data for Science and Technology that gives you the textbook numbers that you find for all the fundamental constants. And so they were 73 sigmas higher. And in 2004, they had the measurement withdrawn because they forgot this one dc d theta term. So but it is a method, and you will see more about this method shortly. So let me summarize all this here, so you get a little bit of an overview of this. So we have static deflection, 1798, Cavendish method. Downside, you have to measure angles accurately, absolutely. Time of swing, you don't need to measure angles, just measure frequencies, but you have to worry about the unelastic property of the fiber. Angular acceleration servo, here you measure angle again, you measure basically the acceleration of the angle, but not of the torsion fiber, of the turntable. And electrostatic servo, where you have to measure a lot of stuff, voltages, capacitance gradients, and so forth. So now you say, are torsion balance the only thing that I can use to measure gravitational constant? No, you can use other stuff. We have seen plumb lines and normal pendulums. I show you one other one because I'm intimately familiar with it. You can use a normal balance. And that also has an interesting teaching moment for you too. So here's how this works. So you have two large source masses and two test masses and a balance. You connect one test mass to the balance, you get a point. You connect another one to balance, you get a point. You connect the first one to balance, you get a point. So now you have a weight difference, right? And this weight difference can be just because they weigh differently or what have you. Now you move the field masses and you repeat this now, and now you see that the lower test mass now is suddenly lighter because there's a gravitational pull to the top, right? So balance ring goes down. Whereas if the upper field mass, it's upper test mass, it's heavier, and so forth, right? So now in the position apart, we had this mass difference. In the position together, we have the different one. You do the same thing again, and you get here this difference, right? So very, very simple. So now you can now solve this equation that we have seen before in a different way. So you can say, okay, my G is now this force, or this force difference here divided by R squared over M. So here's the signal. And so this is 1 kilogram masses, and the signal is about, amongst friends here, 1 milligram, right? So that means a part in 10 to the 6. So you can change this local G by a part in 10 to the 6 by putting these source masses up. And I will show you briefly what these source masses are, okay? But before, I want to address one concern that you guys have. You will say, but, well, this is in gram, whereas this is in newtons. How do I convert this? Well, I need a little g, and then I can convert grams into newtons, right? So this is easy done, and we can measure little g to a few parts in 10 to the 8 at the time. And this can be done by just dropping a mirror or something in a gravitational field and measures local acceleration. So now you ask, what are these source masses made of to change the local acceleration here at the position of the test masses by a part per million? Well, what is a dense material that you guys like? Well, lead is be good. Lead has a density of 9. So the problem with lead is you need a homogeneous source mass. Okay, so what we used is mercury. 13.6 tons of mercury is only a cubic meter. Isn't it much? So this is when I cleaned the experiment up, so I had to take all the mercury out. I'll show you another fun picture about this here. So if I appear crazy to you, that may be the reason. So mercury is sold in units of flasks. So this is a flask of mercury. It's actually traded in the Chicago Mercantile. So there's a stock price every single day. The mercury price fluctuates. So when we did this experiment, the mercury was leased, and the leasing deal was at the end of the experiment we can sell it back to 60% of the stock price. Well, the mercury price went through the roof, and the University of Zurich made money on this deal. So we had 400 flasks. Each flask is about 39 kilos that goes in there. Yeah, here's this, and here's here. This is how I laid out the list of the mercury. I mean, everything was done on the vacuum, just a little rest I had to do by hand. Yeah. Okay, so now let me show you about why are we still worrying about big G to this day. Why I'm telling you all this stuff about big G. Well, big G is not very well known. So these are now the experiments that have been carried out in the last 40 years. Okay, and there's a little bit more than a dozen experiments here. And you see, this here is about 700 ppm. Okay, the scale here. The smallest experiment, this is the Siemens-Gundlach experiment, 13.6. Here's about 11 ppm. But you see the scatter between the data is enormous. There's a huge scatter between the data, right? So we at NIST, part of our mission is to measure fundamental constants. So this is our preview. So we looked at this and said, well, what should we do with this? Yes, we can do a new experiment, but the data situation does not get any better, right? Because if you add another point, you have a crappy data set, and then you have a crappy data set plus 1 point. So nothing is gained, right? So we said, maybe we can do a redo of some of these experiments. So we talked to the people, and sure enough, those right ones, the ones in red, they were measured at the BIPM. So the BIPM is this International Office of Weights and Measure that's outside Paris and Sèvres. This is where the international prototype of the kilogram is. They had performed this experiment in 2 different iterations, 2001 and 2013, and published these results. And they said, you can have our equipment and remeasure it. Let's do it. And this is what I tell you now. Okay, so, and this is also now, I think I'm my 6th year on this project now. So here's how it works. You have a torsion disk, and in a torsion disk are 4 test masses. They're about 1.2 kilograms. They're made out of copper. And here's an aluminum disk, mirrors and stuff like this. What is important later on will be the moment of inertia of the disk with respect to the masses is only about 10%, 11%. The period is about 121 seconds. So far I have not shown you the source masses. Let me show you the source masses. The source masses are outside, so there's a vacuum envelope in between. The stuff that I showed you before is inside the vacuum. Outside I have 4 source masses, and I have 2 types of source masses. So the original source masses came from Paris. It was 11.2 kilograms, also made out of copper. The concern that people had with this is the following. If you have 2 copper masses that are in a room like this, where there's a lot of 60 hertz electromagnetic stuff, you get an eddy current interaction that could be attractive between the copper masses, and that's why they measured higher. So we got a second set of source masses made out of sapphire, because sapphire is not a conductor, so there wouldn't be any eddy currents in there, so we could remeasure that. They live on a Bode circle radius of 240 millimeters. The inner ones live on a Bode circle radius of 120 millimeters. Okay. I mentioned to you before, and this is now where Dahl will be super happy, that these torsion fibers have this problem with the Q and the elasticity. Well, these people in Paris thought about this, and they used a strip for a torsion fiber. Yes, because you get that famous dilution. So that means part of the restoring torque is elastic, which has loss, and then the other stuff is conservative. The way I usually explain it is the torsion disk rises a little bit up in a gravitational field as it rotates and comes back down, and you get the money back, right? This is a conservative force, so this doesn't have any loss. So the loss is over 100,000, so we can be good to 10 ppm. So there's not any worry. It's made of copper beryllium. And it has to carry all this load, right? I mean, it's a relatively heavy torsion pendulum. It has 6 kilogram active load, active mass. So, and then we do also here, as you know, the Cavendish method. We've seen this before. So here's how it's done, right? I mean, I move this in this counterclockwise position, and I see the pendulum swing here, and then I move it in the other position, and it swings down here. And this difference here, 152 microradian, is my gravitational signal that I use then to measure big G. And in this case, this mass integration that I call just K1 and K2 is here 35 little r to the 4th divided by r to the 5th power. So this is because of the quadrupole system that I have here, right? The 4-fold symmetry, I get here r to the 4. So, and then I measure the moment of inertia. I put this all in here. And the moment of inertia is mostly my four masses and a little bit of disk. And then if I solve all this, this is my G, my gravitational G. Right? So I have to measure angle difference, frequency, this radiuses, this masses, and then this ratio of the disk to the moment of inertia of the four test masses. But it also has electrostatic measurement, which I told you before also. So here we have to measure voltages and capacitance gradients. They call it here K, and of course the geometry and all the stuff. So if you put these two equations together, you see here the interesting thing about this. So this is one part that makes the experiment very powerful because you have these two measurement methods and they have different dependencies. For example, phi. So here phi occurs here at the numerator, whereas here it's the capacitance gradient, so it's in the denominator, right? So this, if my autocollimator reads off by 1%, this number would be off by 1%, and this would be off by minus 1%, right? So it's nice. This depends only weakly on m, because m only shows up here, which is about 0.11. Here, it depends on m, little m. This is the mass of the test mass. This one depends on R2 squared mostly, right? There's a little more R term here. This one depends on R2 minus 4, right? So there's a lot of checks and balances that I can do here, which is kind of nice, right? So if the numbers match up, then it's cool. One thing that I want to expand a little bit, and this is important for you to know when you see later on the data, let's look at this thing again with the phi, okay? So I simplified this equation a little bit here for you, but what you take away from here is here's the phi is on the top and the numerator, here's on the denominator. So if I write it like this, my G Cavendish is proportional to phi, and C1 is the proportionality constant. So if I do error propagations, you see that my sigma squared, my uncertainty of the big G is just like C1 squared divided by C phi squared, right? So this is regular error propagation. And for the servo, I have it on the bottom. So I get it like this, right? So very easy. So if I now build an average, I can do the regular error propagation and I get all this stuff here, right? You see now here is I have C1 squared, C2 squared, and then I have here this cross term, right? And this one, I can write this G over phi. This is the G0 over phi, and this is this thing over phi. So if I plug this all in, you see if I get the same results, it is independent of phi, right? So I can measure big G independent of my calibration of the autocollimator if I take an average. And that is a nice advantage. But on the other hand side, if I look at the difference, in the difference, I don't get this negative sign here, I get a positive sign. So I get 4 times this uncertainty, right? So for example, if my uncertainty of the autocollimator is 50 ppm, then I could measure a difference of 100 ppm and it could still cancel here, right? So it is possible that I get 2 different G values by twice the uncertainty of my autocollimator and still have a coherent data set, okay? That is important. The masses are just a linear relationship. Let me go back here, see this too here. So the masses are only here linearly, right? M. So if you want to measure this to part 10 to 5, you have to measure the masses to part 10 to 5. So that is easy. And I showed it to you also how much we measure masses. One thing that's hard is though the geometry. Okay. So this is, and I misspoke when I said the quadrupole, it's actually a hexadecapole relationship. And you have to measure this 120 millimeters with a really high precision. And for that, you need a coordinate measurement machine, which is slows the experiment down a lot. And here you can see how well we can measure that stuff to about 10 ppm. And because you get here 4 sigma r over r, right? And here 5 sigma r over r. So you have to measure this to like, sub-micron position. And this is one thing. So I didn't do the CMM part of this work. We have experts at NIST to do length metrology. And when the experiment came from BIPM, the first thing this guy said, with these test masses, I can't give you a center of mass determination to this uncertainty because the test mass that you handed me is a potato. And I need a cylinder. So we had the test masses made from scratch, from new diamond turn and all the stuff. So because you need to have a form that is good enough to allow the determination of the sport circle radius. Okay, mass measurements. So here's my friend from mass group. So we measure the test masses to 5 parts in 10 to the 8, plain enough. The test mass to 2 parts in 10 to the 7, and the sapphire mass to 4 parts in 10 to the 7. So these are kind of weird masses. They were close to kilograms, so they could measure very precisely. They had 12 kilograms. That was kind of a little odd number, and they are 6 kilograms, so the uncertainty is a little higher here. What they did is, though, they added a blind. because the problem is when you repeat an experiment, you want to stop when you either measure the literature value or the previously reported value. And I didn't want to have the psychological trappings of having every day to say, oh, I'm off, oh no. So I said, just add a blind number. And so the number is between -1,000 and +1,000 ppm. It's in this envelope. And my boss used to joke is that this envelope has a frequent flyer pass because he was going to so many conferences because my boss was carrying the envelope because I was saying, I'm going to open it up this conference, I'm going to open it up, I'm sure. And then I always backed out because I wasn't ready to open it up. But we opened the envelope just a few months ago, and I show you this to you also. And I was almost ready to back out, but we did it. So we went ahead and did it. So I was measuring the stuff for a long time, and you know what? Stuff just did not convert. Okay, and one day I said, this is a random number generator. This experiment doesn't make any sense. Let's give it up. It's just horrible. And one day I said, let me plot the entire data set of a year. And I did this. So here's the plot of the entire. This is still of the random number, so don't worry about the number. So here's my big G measurements. Here, this is in red, in copper masses and sapphire masses, and the light blue is my pressure in the chamber. So the chamber that I got from the BIPM is an old vacuum chamber. It's leaky as hell, so it slowly kind of leak up after my pump downs, okay? And what you see here is there's a correlation, right? Vacuum pressure goes up, big G value goes up. I'm gonna, what's going on here? So let's investigate. So I flanged this stuff up. So I have a short connection to my turbo pump and have a little valve, so I could change the conductance to my turbo pump, and I could basically run this as a controlled experiment, okay? And here's what I measure, all right? So here's the pressure in pascals, and this is now in torque and not in big G, but it's the same. And you see it goes up here in a very linear fashion, and then there's one point that is not on a line, and I will explain that point to you, don't worry yet. There's a pressure dependence. So now you wonder, how does the torsion balance know about the pressure, right? So how does it know where the source masses are on the outside? How does it all work, right? So, and I figured, well, it must be a temperature effect as well. So I installed little heaters on the outside where the source masses usually would be. So the source masses would sit on these things on a carousel. I took them off. I installed heaters here. And now instead of moving the source masses around, I just heated, okay, in the same kind of pattern that I would move the source masses. So, and again, here's the pressure. Here's the heater. So when the heater is in a clockwise position, I get this torque difference. When heat is in the counterclockwise, I get this difference. And here's again the large point that large pressure is off, right? So it is an effect that requires a temperature gradient and pressure. So how does it work? Well, it works relatively easy. So if you have a gas, and there's a test mass in the gas, and there's the same temperature, the same pressure on top of the bottom, these gas molecules will hit this test mass, and the momentum imparted on the downward direction is the same as on the upward direction. So there's no net momentum, so there's no force, right? Okay, let's make the upper gas a little bit warmer, right? And this is the nice thing about a thought experiment. Oops, like it's easy to do. Oop, so the warmer, here's colder. So now you see the Maxwell-Boltzmann distribution here shift a little bit to the right, a little bit to the left. So the momentum that's imparted here from the top is a little higher than the momentum imparted here from the bottom. So there is a net force in the downward direction, right? And in fact, if you look in the literature, there's this guy Waldman who has written this up in 1959 and is given for a spherical test mass an exact equation, okay? And so here's what's important, okay? So here's the temperature gradient. So this is the dT dz. Here's the pressure in a chamber, and then here's L. L is the mean free path between collisions. And this is a minimum number between, if you have an infinitely long, big system, how long it takes for a gas molecule to bump into another one, okay, which I call L infinity, or the dimension of the system. And so now you can look at this, what is this dimension here as a function of pressure? And you see here, it goes at high pressures, it goes to 10 to the minus 1. So at high pressures, this equation doesn't work anymore because this P and L, they cancel each other. Okay, as the P goes down, L goes up, and vice versa. But at low pressure, L bottoms out here at the L dimension, and it's only proportional to P. So this is exactly what I've seen with my data. At low pressure, I get a force, or in my case, a torque that's proportional to pressure, and at high pressure, it bends over. So All makes perfect sense. Even this, the scale, everything works out. So what I got from Paris is not a torsion balance. I got a gradiometer. So I have this gradiometer, and I'm supposed to measure big G, right? So now I looked at this a little bit more careful, and I haven't shown this to you before. This is kind of a side view. Let's focus on this first. So the test mass is really close to the vacuum wall because you want to bring the test mass close to the source mass, right? So you have maximum gravitational interaction. So there's only like a millimeter or so gap, and so is on the outside. And this wall thickness is about 4 millimeter, and the vacuum has this overhang. Okay, so what I did now is I installed here thermometers, and I could measure the effect. The temperature changes as I move the source masses around, and there is an effect. It changes by several millikelvins. And that has to do with because my system is in a temperature-controlled room with a downdraft, and when the source masses move, it changes just the flow pattern of the air, and this is why there's a temperature gradient. So that was my problem. So I thought, how can I fix this? So my first idea was, well, I need better vacuum. So I changed the chamber and put a lid on that has a big flange. I put a pump on top of the lid, and I could make the vacuum pressure better by a factor of 10. But the problem is I made the temperature gradient worse because now I have this heat source up there, a 500 watt vacuum pump. So everything went to hell. So in the end, the better solution was to make a small delta T and have the pressure outside the box. So you're going to put some insulated boxes in there, put the pump out there, and then I can do it. And I can still change my P to make sure I have absolutely no effect. I can still prove that I have no effect. Okay. So then we opened this thing, and I told you why I was so nervous about this, because when I was looking at my data analysis, my G value was so far out. It was a really high value of big G. So the only way I could have a reasonable big G value is if the number in the envelope, and this is weird that I think about the number in the envelope, I should not be thinking about it, but if the number of the envelope would be negative and large. And who in their right mind would put a negative large number in an envelope, I was thinking, right? So I'm thinking, I have to back out. This is not going to work. It's not going to work. But look at this here. Here's the number. Minus 650 ppm. So we open the envelope, and from now on forward, I show you all numbers with the open envelope. So here's the result now. So here I have measurements of the copper, Cavendish and Zerbo. And the copper masses, there's also one concern about the density homogeneity. So you have to measure it on 3 orientations, and this depends on how much inhomogeneity there is in the copper. That all makes sense. And then here are all results. So I have copper Zerbo, copper Cavendish, sapphire Zerbo a little bit lower. Actually low. I would have liked this a little higher, but I can't change it. This is the number I measured. And here's the sapphire Cavendish. If I average all that stuff together, and here's the contribution to my mean value of big G, all right, then it looks like this. So it's a little lower than I like, but this is what it is. This is where the dice fell, so it's definitely better than this, but it's still, on the side. If you replot this plot, and I have done this without these points here, it seems almost like there's a hard wall here because all the points are kind of lower than this, or I don't know how to say that. So what is the current status? I have still a few bookend measurements that I want to do, and I'm on track to get everything done by the end of the year, right? So I have little things to take care of, little nuts and bolts. So this is not my work all by me alone. So this is actually my last slide. That's why. So I'm working here with Dave Newell, Vincent Lee, who's the quantum measurement machine guy, me, Leon Chow, and Clive Speak, who originally did the original experiment also. And we're posing here in front of a crane because one of the outcomes of this experiment was how to safely move a crane. Yeah, I'm not kidding. So thank you for your attention. Yeah. Yeah.
So in that context, do you worry? That's a question, I guess, in your way first, but I'm also just interested in what concern there may be if there's any about complementary bias.
Yeah.
When you're making precautions.
I mean, the thing is, this measure was really blind, right? So I can't, a lot of people, so there's this famous story. I don't know if you guys should know this, right? Or optical people, the speed of light. Who knows the story about the speed of light? So the speed of light was first measured by Michelson, one of the great ones, right? So he measured the speed of light, and everybody after him measured the same value for the speed of light. Well, Michelson's measurement of the speed of light was wrong, because he took into account, I think, the wrong viscosity of air, something. There's some air parameter that he had wrong, and that was only discovered at World War II when people measured the speed of light with microwaves and didn't use optical thing. So there's definitely this what people call intellectual face locking, right? You look at some stuff and you want also something to happen, right? So the reason why I don't like it, because I'm discrepant with myself. So my old thesis value is here, and here's the new value, and so now how can I live with two discrepant values? So well, that's why I don't like it. But on the other hand side, I mean, the dice have fallen. This is my best work that I could do with this experiment. I think, and I'm also not sure what will happen to these points, but I clearly could show that this temperature effect will have affected these data points, right? So I think something has to happen with these data points, because the other thing, if people carry the data points on forever, then it doesn't improve the overall mean value, right? So yeah, I don't know. It's so I'm in contact with these people who did the original measurements, and I told them all about this effect, right? And they said, "What is your vacuum pressure like?" We don't know. So they don't have any recorded. There's no records about what the vacuum in the chamber was. There's maybe a photograph where you can see a vacuum gauge. They don't know what the other thing is. When I did all these experiments, it depends also on the pattern that you set up in the lab in terms of the air currents. So, that this effect that I have, so and so many nanonewton meters per whatever Pascal or something, depends exactly what the temperature gradients are. And it's really finicky, it's small temperature. So the temperature gradients that I measure at the vacuum can are of order of millikelvins. So it's really, really tiny temperature gradients. Yeah, so that would be, if you redesigned the experiment and if you spend another 10 years doing it, that would be the way to go. But I honestly don't think that this experiment is all that clever in the design to begin with. So I'm not sure if you want to really, there's G experiments that are much more clever than this one, right? But yeah, that would be a good idea. The thing is, why it's difficult to do is I did a lot of stuff, for example, the copper source masses. The big problem is they could have a density gradient. So what we had to do is we had to rotate those in 120-degree increments. Every time you rotate those, you screw up the positioning. So then you have to have the CMM, the coordinate measurement machine, measurement again. And if you do this in vacuum, that means you have to break vacuum, rotate those, do the coordinate machine measurement, close the vacuum. It is a process, right? So, and do you really want to do that, right? Or do you want to just design a new experiment? Yeah.
Is uniform. So your copper cylinders.
So for the copper cylinders, the expected thing is about 20 ppm. This is what I see. When I showed you this, let me go back here. See that this thing is about 20 ppm, and this is what also the calculation gives me. So we have measured the inhomogeneity of the copper masses by putting on an air bearing and letting them oscillate to figure out, and that is consistent with what we got here. Yeah.
Static charge.
Static charge. So between the copper masses on the inside and the outside, there is a vacuum shield. So there should not be anything communicating. No, because it's a Faraday cage. So there's this plot here. Yeah. The outer masses are on the outside here. Then here's a 4 millimeter vacuum wall, and then here's the inner side. So if there's charges, that doesn't get through. But that is one of the things, the experiment hinges upon the fact that nothing communicates the source mass position to the test mass position on the inside of the vacuum. But this temperature pressure effect communicates this, because you heat the vacuum wall differently if the masses are here or not, and then you have this, gas pressure effect here. That is it's really important that there's no other physics that communicates your source mass position into your sensor.
On that final chart where you show all the different values, including your newest one, what was the setup of the experiment of the one that's almost directly beneath your newest one? Is it a similar experiment? Is it Cavendish?
This is a Cavendish.
Yeah, okay.
No, this is a Cavendish.
Okay. And then the second question was, how good is good enough for G? At some point, what is the real advantage of going to one binary other than just sort of scientific curiosity?
Yeah, so that is a good question. What is the motivation to all this, right? So big G is not important at all, right? And because what you measure is always in astronomy, what you always need is big G times the mass of the central body, right? So we know big G and the mass of the Earth extraordinarily well. We know it to 8 digits or something, right? So if you measure big G, you can measure the mass of the Earth. So in fact, the best measurement of the mass of the Earth comes from these experiments. But so in all astrophysical things, it's always G times M. There's a few processes where big G matters. For example, the neutrino luminosity from the sun depends on G to the 7th power. So, if you change G by 1%, because the neutrino flux changes to 7%. So that is a big thing. But most of the stuff is not interesting. So it is like Mount Everest. Why do people climb Mount Everest? Because it's there, right? So it's a difficult measurement and you want to do it and you want to have good agreement. The other thing that I find interesting is most of the stuff is used in other physics. So for example, these electrostatic measurements that I showed you, where you have all these capacitance gradings and all that stuff, is used for small mass metrology. It's used for laser power measurement, where you bounce a laser beam off a mirror and you measure the force in the mirror and you electrostatically zero the mirror back. So if you understand that physics well enough, then you can also trust that well enough for other measurement schemes. And I think, so this measurement has, an uncertainty of 11 ppm, right? So people are trying to crack the 10 ppm mark, right? So they have single digit ppms, but I don't think it's worth it, right? If you have that much scatter between the data points, right? And so, but I feel like if you could X these data points away, and then these ones, they have large enough error bars that you can say, yeah, within, 2 or 3 sigmas, they would agree. And then there's a few that are troublesome. But I think it's most important to have a consistent data set. And if the consistent data set, the average is, put to, 4 digits, I think that's all we need.
And then sort of follow on that may be a bit naive, but is there a sort of theoretical limit to how fine we should ever be able to measure it? Is there some fundamental reason why we might not be able to go past 10 to the negative 14, 10 to the negative 15?
I don't know. Yeah, I don't know. I mean,
Okay, a different question would be: is there a certain sig thing at which you could discover new physics?
yeah. And so I'm involved in the big cheap thing a long time, and I say about once a month I get an email from someone says, "Oh, I can explain all this data. This is what it is, right?" And all the stuff that people say would be so much easier to measure in a null experiment, right? Because if you want to figure out is it in a sphere law, you can just make a null experiment, right? And people say, "Oh, this has to do with there's some whatever where the Earth is in its rotation around the sun, it changes the field and something, and then big G changes it." If that would be true, little G would change also, and we know little G to a part of 10^8, and we have continuous data sets over multiple years, over decades. And there's no such thing where little G changes by a part of the 4, right? So I don't think that it works. And then say, "Oh well, little G." Then they have other arcane theories why little G would not change, right? But that doesn't make any sense, right? So I think certain things you can have dedicated experiments where you look at G dots, right? That's the G change of time, or you can have null experiments. If you compare absolute numbers, they're taken in different labs with different methods. You just and I think this is the biggest problem with this plot is So there's 3 things that could explain this stuff, right? Either there's new physics that we haven't taken into account, and maybe with the, this thermophoretic effect that Waldman wrote, this would be physics that hasn't been taken into account, right? So that would be one explanation. The other thing is that people just estimate the uncertainty is too small. Meaning there's nobody who looks over the lab and says the uncertainty is really right. I mean, you do a good job, but you could have forgotten something, right? There could be what people call a dark uncertainty that the researcher has not thought about that needs to be built into these experiments. And then the third option is that it means that these data points are just all consistent, but the uncertainty is much larger, or the number is just plain wrong, right? So the uncertainty is right, but there's just another measurement bias that we don't take into account. Yeah.
Is there anything in the astronomical observations, for example, from neutron stars or quasars or the black hole collapse, that you could use to back up the gravitational constant?
No, it's all GM. You only get G times the product of that. So.
Do we have any measurements where exactly the same test has been performed with the same equipment, but it was disassembled, reassembled, and completely reconfigured?
That would be the experiment, right? That would be the first. Yeah. But, I had to throw out the potatoes.
It changed them to French fries.
Yeah.
Kind of a more practical question. In these kinds of measurements, what is the thing that kind of limits the speed at which you can do it? How much of it is the figuring out the theory versus manufacturing the equipment and learning how to operate it?
So on this experiment, that's the real science data, right? The data that goes into this number in the end, that was taken probably over the course of I would say 3 months. But the uncertainty stuff that took years, we have to do all this and that, and this and that, doesn't depend on magnetic fields and temperature and this and that. So that takes a long time, right? So on this experiment, you can get a relatively decent data point statistically over a week or so. So that's all you need, right? But then all the uncertainty and manufacturing, building it. I mean, if you design an experiment from scratch, it takes a long time. So Indiana University has a new Big G experiment going, and they started working on it, I think, 5 years or so ago. Right? I think they're in the second NSF grant right now, and they still haven't, published any data. And so, I mean, on average, these experiments have, about 10 years is a data point there. And so this very best experiment here was done in China, HUST, Wessing, there's a science technology, and they have 100 people working on Big G. And they produced these 2 data points here. Yeah.
Are all of these systems sort of classically based, right? We're talking a lot.
Yes, one atom interferometer, this one here, but it has relatively large uncertainties. That the problem is, an atom interferometer still has all these problems of the conventional systematic effects, right? And you still have to worry about. So a lot of the things that I think is also a big problem is the homogeneity of the source masses. Because when you take a metal source mass, the density homogeneity is about a part to the 4. And a lot of people don't know that. And then especially some people use tungsten, because tungsten is very dense material. So in the Big G, the name of the game is to get a lot of mass close. And one way to do this is using a large density, right? So tungsten has a density of, I think, 21 or so. But it's a sintered material, so the homogeneity just sucks. It's not good. That's why in Zurich we use the mercury, because the liquid is very homogeneous. Then here the sapphire, single crystal sapphire is very homogeneous, that's good. But yeah, there is a new material, it's a tungsten oxide that is optically clear. It has a density of 9. That is nice because you can use the optical clarity to figure out density problems. But the choice of the source mass is really important, and I'm not sure if they have been all considered well. The other thing is I have a lot of doubts about these 2 experiments down here. These are the ones that still have this Kuroda effect, and I told you the Kuroda effect will produce numbers that are higher, but they have been corrected down to take into account the Kuroda effect. And I wonder if people have really used the right cue for that, because there's also the experiments have been done, and then 10 years later or something, the Kuroda effect came out, and then they corrected it based on some. Who knows where the Q came from, right? So, yeah.
I think we'll stop there if anybody has any more questions. Yeah.